NMOS beyond discovery and registration, an open solution for control and monitoring. So I'm betting most of you out here know NMOS already. Just to be sure we're all talking about the same NMOS, we'll go over a couple things. So network media open specifications, it's the open source special sauce that enables vendor independent control of your IP video and audio gear, whether you're using SD2110 or IPMX. So you're probably using NMOS, and you might have even contributed to it. I know folks out there have contributed to it. And today we're going to look at what's beyond what you're using right now, and a special focus on NMOS control and monitoring. That's the main scope for today. And do we have slides up too here?
Yeah, I can't see the slides on my end either.
Yeah.
This might be tricky.
Great. And can we have Cristian on one screen or no? What do you think? Cristian on one and slide. Okay, we're going with it. All good.
I can't see the slides on my end though, so I don't know what you were presenting.
All right. So just to level set and recap what it is and what it means. What is it? It's a family of open source, free of charge specifications that enable interoperability on the control layer for media devices on an IP infrastructure. So what does that mean to you? Well, end users, SIs, you, everybody, we get to create the best of breed solutions from a greater pool of vendors. Equipment from different companies can all work together. And since it's an open set of specifications, there isn't vendor lock-in, and that means you can use the equipment that you prefer and build the system that best meets your needs without being tied to any specific manufacturer. So all of this, as Cristian said really well, it removes the proprietary barriers and fuels competition. So thinking big, the NMOS vision is something like this. It's where we want to head. It's what this might look like. You take a device out of the box, plug it into your network, discovery, registration, connection happen, and then you can approve the device. And assuming you've had a device like this in the system already before, maybe a frame synchronizer, for example, then you go to the management console, push a button, load the config into the device, and start making use of the device right away. The control system will know it's there, and you can start using it. You can control it using NMOS control. So that's the vision, that's the direction we're headed. So looking at the NMOS ecosystem today, you already know about NMOS, ISO4 and ISO5 discovery, registration, connection in an IP environment, but there's so much more to the ecosystem, and I just love this diagram, this representation of the NMOS layers that Cristian put together. You can see the whole ecosystem here, and all the possibilities. So this is a view of the functional layers within NMOS. The NMOS themes, the layers, you can really see how everything in the ecosystem is tied together, and you can clearly see which specs are related to each other and how everything works together. And when you look at the website, you're going to see that the specs are organized in exactly the same way. So you see the resource management, connection management, the device control and monitoring, that's what we're going to focus in on today, and device configuration and security recommendations, all working together. So while the scope of our talk is primarily around control and monitoring today, you'll see that the NMOS testing framework is an open source way to eventually cover all the specs and the layers. And what that means is faster troubleshooting and maintenance. And with the standardized testing framework, I'm talking about the green line at the bottom there, that in this diagram is all about ways to test the interop test method. And Cristian's going to get into some detail on that. So in talking about NMOS control and monitoring as an open solution, there's several key aspects of the platform. So one, security. NMOS is built with security in mind. It's secure by design. Also, the NMOS architecture and roadmap are owned by the NMOS community, which is ultimately responsible for its developments. No one single person or entity owns it. The community owns it, and that's really the spirit we're going for, that open community vibe. There are a lot of open forums, Slack channels, GitHub, regular incubator meetings, and those are available for vendors and users and integrators to address any concerns or improvements. So another key is that interoperability testing that's part of the NMOS testing framework. And this framework's been used by many of you probably at the past JTNM tested events, and you'll hear more about this in a few minutes. Another key is the NMOS customized control and monitoring. So NMOS allows for detailed control and monitoring of devices within the network, and you can customize device control according to specific production needs. So as a vendor or as an end user, there are standard minimal NMOS building blocks that you can start with, and the controller can discover any vendor-specific functionality in a standard way. So today, you're going to get a look at the four main themes, which we believe are the key distinguishing attributes of the NMOS control and monitoring solution, the open and transparent nature of the process from start to finish. This is an open and transparent community, and everybody's welcome to participate. The flexibility of the solution, the tangible nature, so all the deliverables and how easy they are to find in the public domain, all the specs and artifacts are free to use, and the modular approach, which allows us to further explore and deliver other pressing user stories and needs. So if it's okay, I want to share a bit about the whole process of delivering an AMWA activity in an agile and iterative way, and the community's involved at every stage. Sound good? All right, first, we start with a set of industry problems presented by the community during regular NMOS incubator calls, and these problems get refined into user stories. Then, a subset of community members, main contributors, involved participants, they take those stories and onboard as part of an activity proposal. So each activity has representatives, both end users and vendors. And next, the NMOS steering group offers governance and guidance while time boxing the activity and making sure clear deliverables are set. The NMOS Architectural Review Group gives guidance throughout the sprint, which finishes with a set of deliverables. And at this point, some of those may be already available in the public domain as WIP. Typical activities take more than one sprint to gather enough user stories to meet the criteria for publication. And regular progress is offered to the community as part of the NMOS incubator calls every 2 weeks. And then beginning of each sprint is another opportunity for the wider community to refine the user stories for the next sprint. So at the end, most, if not all, of the final deliverables are made available on GitHub in the public domain. It could be artifacts we create out of a sprint. It could be an activity. It could be anything. It could be a specification, a test suite, an open source implementation, a how-to manual, a guide. All of these end up in the public domain, and they're tangible. You can find them. You don't need to pay for them. That's the process. Cristian, over to you.
Thanks, Cindy. So when building out the area of control and monitoring, we had to carefully strike a balance between standardization, interoperability, and maintaining vendor freedom. So we explored the problem space from different angles and decided that the best approach is to document the solution in different layers or tiers, which helped us maintain flexibility, but also make the solution modular and decoupled. So on this slide, we're basically showing the whole stack of different layers. So we start with the architecture, which shows the vision, the philosophy. We have the modeling framework, which expresses the language that we want to use, the building blocks, the control core classes and data types, and establish how we can discover these. Then we have the standardized control protocol, which exposes how we can interact with the models, what the commands are, the notifications, what the transport and message encoding is. And finally, in the green bits, you'll see what we describe as opt-in models for specific feature sets. At the moment, we're looking at receiver monitoring and sender monitoring as separate models and behavior that end users and other vendors and integrators have agreed on that we would like to see as further conformance. Next slide, please. So, with the modeling framework, we've tried to bring convergence on minimum baseline models, whilst allowing custom vendor behavior. In this example, we see the NC object class, which all other models must derive from. This is followed by an inheritance tree where models get more specific and detailed. Vendors then have the freedom to use standard classes like NC receiver monitor, for example, directly, or derive it in a custom vendor class which maintains the baseline functionality whilst adding further custom features. In a similar way, we expect vendors to create their own worker classes which derive from NC worker. All vendor-specific models at the end inherit at some point from a standard model. Next slide, please. So, this diagram shows the device model example, starting with the root block and continuing with other branches of models exposing different areas of functionality inside a device. The IS-12 protocol generically wraps around these MSO5 models. That means once we implement IS-12, exposing new models by vendors is done with ease. It doesn't require further work at the protocol level. IS-12 is an operational control and monitoring protocol with fast response times. It's reactive. It provides immediate notifications. And as you'll see in the top right corner, the messages are fairly compact, but they are still readable. Next slide, please. So, what does this give us then? This slide shows an existing controller implementation discovering an MSO5 IS-12 capable device, including its vendor-specific elements, without any prior knowledge about the specific device in question. So what's the bottom line? Well, this establishes a solid contract of expectations between nodes and controllers with regards to model interactions. Next slide, please. Right. One way of nicely representing all of these layers is through an onion diagram, such as this one, showing how a device implementation might look like. We obviously have the architecture, establishing the principles and the background context. And then if we start from the center, we have the framework capturing the core models for both control classes and data types. Moving towards the outer layers, we then have specific feature sets. These are opt-in specific models which only devices which offer these capabilities implement. The next layer out is represented by all vendor-specific models a vendor may create and include in their device. And the final layer is the protocol wrapping, which offers the means to expose models contained within. Now, we think as we progress with adoption that vendors and users, system integrators, will start to see overlap across vendor-specific models with well-defined functional areas. And we encourage proposals for moving these shared functional models from the vendor-specific layer into feature sets containing converging best practices in these areas. So now on the next slide, Cindy will talk a bit more about the tangible artifacts and benefits of our ecosystem.
Most, if not all, of these deliverables end up on the public domain on GitHub. And most of the time, early WIP versions are made public from the first couple of iterations. So looking at the deliverables for NMOS and monitoring and control activities specifically, you can see the NMOS control architecture, NMOS control framework, the control protocol, and the receiver status and sender status. If you feel like it, QR code will take you to all those. And here, this is great for you. Most of the time, an activity doesn't just produce specifications, but it also gives you further developer resources and tools to help with adoption. So in this case, there's a comprehensive implementation guide for NMOS device control, and that looks at both the node and controller implementations and what the expectations are. So QR code on the top will take you right to that if you feel like it. And then we also have the NMOS device control mock, and it's an open source Node.js mock application which offers full MS-05, IS-12 implementation in TypeScript. So second QR for that. These are great places to get started if you want to jump in. And then finally, NMOS CCP, the most used NMOS open source library. It has full support for MS-05 and IS-12. This is the place to start. If you want to get going on NMOS, you can get the implementation guide, the mock, and NMOS CCP right here. So finally, how can you claim any sort of interoperability between multi-vendor implementations without a thorough test suite? So Cristian's going to give us more information on the comprehensive test suite that comes with NMOS control, including the framework core model conformance, the IS-12 conformance, which is including commands, responses, subscriptions, notifications, and error reporting, and feature set model conformance testing, behavior testing, and vendor-specific models to ensure compatibility and interoperability. Cristian, over to you.
Thanks, Cindy. Yeah, this is a great tool for everyone to use, starting with obviously end users when they get a device, through the doors and they want to test for conformance with regards to NMOS APIs. Obviously, we want all end vendors to try and use these in their development pipelines and their continuous integration chains. This is a tool that can be spun up, that can be run headless without actually a UI. You can run it and run it as part of your build processes. So it's very comprehensive. You can pick which suites you want to test for, obviously depending on what your device implements, and it will just help you find issues early on. If you think about, a car assembly plant, you don't want, a specific part to go too far down the chain before it's welded or screwed into another component. You want to catch errors early on. So this provides you with that kind of functionality. So yeah, definitely make use of that. So now we can go to the next slide.
There you go.
Thank you. So previously we talked a bit about the modularity of our solution. The multi-layered decoupled approach, showcased by the onion diagrams before, allow us to mix and match layers to best address the target user stories. So in this example, the onion diagram peels off the IS-12 outer layer and only shows the model layers. And we'll find out on the next slide why.
Next slide's up.
Okay, so what if the user requirements are focused on retrieving bulk configuration, restoring bulk configuration in order to speed up provisioning workflows, enabling end users to more quickly make use of their assets? As the user requirements and expectations are very different from, reactive operational control monitoring, it means we can intervene at the most optimal layer to specifically address these user stories, which in this case means the protocol layer. So in this diagram, we've replaced the IS-12 protocol layer with the IS-14 device configuration API layer, working with the same underlying models, but offering solutions to the newly raised requirements. So next slide, please.
There you go.
There are many valuable user stories addressed by IS-14, starting with the most obvious one, replacing a failed unit with the spare, and then restoring the same configuration on the new unit. Now, another arguably even more exciting one is enabling the ability to effectively serialize entire workflows by serializing the configuration of each cog or piece in the workflow. These can then be stored or versioned, timestamp, and as we'll see on the next slide, they can ultimately be recalled, restored, or instantiated. Now, this provides one of the last remaining key pieces of functionality for fully dynamic facilities, which make optimal use of available resources. So activating a workflow may involve activating new devices, repurposing existing devices which may have a new role or operating profile, or even deactivating devices. Next slide, please.
Slide 20's up.
So finally, both device configuration and operational control and monitoring axes build on top of the same modeling framework. Now, this creates a synergy between these axes. Media functions instantiated using IS-14 can be understood, controlled, and monitored by the facility controllers using IS-12. And any operational control actions performed by the facility controllers using IS-12 can be included in upcoming workflow serializations performed by IS-14. You can then increment the version number of that workflow and recall it later. So now I will hand over back to Cindy for a bit more on how these models actually solve problems.
Cristian was telling me all about how people think in entities, objects, and interactions. They don't really think in bytes, and this diagram really gets into the details on that. And Cristian, I'm going to throw back to you to go into the details.
Thanks, Cindy. Yeah, that's exactly the experience we went through when we looked at BCP0801 and 02. In that activity, when we started looking at, what are the requirements for monitoring a sender, monitoring a receiver, we almost never talked about what's involved in the protocol because we had a protocol. The protocol was an enabler. What we ended up talking 99% of the time was exactly as you said, about entities, about interactions, about what the models need to expose, what functionality we need across all of these device vendors for it to be very easy to use and integrate and make sense in a huge facility. So at the end of the day, these models provide a natural feeling language for the people that solve these problems to come up with solutions, shape these solutions. And then these models can be published using a very simple wrapper protocol like IS-12. That's what this is trying to tell us. So if we can go to the next slide then.
It's up.
So now we arrive to our conformance strategy. And this is what I like to call our snake diagram. So the conformance strategy we've devised in this area of control and monitoring is very multi-tiered. So what I mean by that is that we have different conformance points that we've established to get the right balance between standardization and vendor freedom. So we have devices built with the same language or building blocks using MS5 or 2. Then we have these advertised using a standard protocol like IS-12. And then on top of that, we have opt-in conformance. So vendors can opt in to conform with further feature-specific models and behaviors in future BCPs. These are BCP0801, BCP0802, and there will be other BCPs in the future. or other areas of functionality. And these are very much market-driven, often kicked off by end users in specific areas, like BCP 0801 and BCP 0802. So finally, vendors are very much free to create their own vendor-specific models using this established language or these building blocks. And even the standard minimum models, so like the receiver monitor or the sender monitor, can be implemented as is, as the minimum set, or they can be derived using the vendor-specific functionality, which has the minimum set of functionality and the vendor's custom functionality on top. So I think that reaches the end of our presentation. And Cindy, if you want to say anything more or open the floor to any questions.
Thank you.
Thank you.
And tech department, can we bring Cristian up? Is it possible? If not, it's okay. Questions?